Hello students, in the last lecture we have studied about the coordination number, charge on the complex ion, as well as one more point like the oxidation number of metal atom or metal ion, how to determine that we have studied in the last lecture. Today we have to study one theory, that is Werners theory of coordination complexes or Werners theory of coordination compound. In it we have to study Werner, first of all explain, derive some postulates to explain the coordination complexes, coordination compounds, and the postulates of Werner's theory now we have to study. See, the first postulate of Werner's theory, that is, unlike metal salts, the metals or metal ions in complexes, metal ions in complexes shows two types of valence, shows two types of valence, two types of valency or two types of valence, that is the primary valence or primary valency and secondary valence or secondary valence, So unlike metal salt, because in metal salt the metal shows only one type of valence, but in the complexes or coordination compound, metal ion shows two types of valence, that is the primary valence and secondary valence. Both these type of valence, both the valencies are satisfied, by the metal, Next postulate, that is primary valence is satisfied by the ionization sphere or the species present in ionization sphere. We have studied before it also two spheres are present in coordination complexes or compound, that is ionization sphere and coordination sphere. So what are the species present in coordination sphere? That species satisfy the primary valence. So these species present in coordination sphere are what? That is the anions. So anions satisfy the primary valence which are present in ionization sphere, The secondary valencies are satisfied, by the ligands, which are present in coordination sphere, One more point here you have to remember, that this secondary valency or secondary valence is fixed. That is not changed. Secondary valence is fixed. It is not changed, which is satisfied by the ligand, whatever it may be, anions or neutral molecule present in coordination compound. Anions or neutral molecule present in coordination sphere. So they satisfy the secondary valence. This secondary valence is fixed. But primary valence or primary valency is not fixed. It is not fixed. It is what? That is the variable. Primary valence is not fixed. It is variable. It depends upon the spaces present in the ionization sphere. That is present in the ionization sphere. See another one postulate of this theory, that is number of secondary valence is equal to coordination sphere. That is the number of secondary valence is equal to coordination number. Coordination number. So these are nothing but the postulates of this theory. The secondary valence have fixed spatial arrangement. Secondary valency have fixed spatial arrangement in the space of molecule, in the space of that molecule, that is in coordination compound. It has fixed geometry, we can say. That is, the coordination complex have fixed geometry, which is depends upon the number of ligands attached to central metal atom or ion, as well as what is the hybridization of that central metal atom or ion. So on that basis its geometry is decided, or its geometry. But you remember that secondary valence have fixed spatial arrangement. Means what are the ligands attached to central metal atom or ion, that ligand have fixed arrangement in the space of molecule, due to which that coordination complex have definite geometry, definite geometrical shape. See here one example we will take. That is nothing but what? That is the NH3 by 6 and here Cl3. It is hexaamine cobalt 3 chloride, name of this compound. After this we are to study nomenclature of coordination complexes or coordination compound. Now what happens in the structure of this coordination complex, coordination compound is this one, that is cobalt is present at the center and 6 ammonia molecules are present at what? That is the 6th corner, here like this. This is nothing but the 6 ammonia molecule donate its 6 lone pair of electron to this central cobalt metal. It is the geometry, it is the shape of this molecule. Now this is inner sphere, this is the inner sphere, which is coordination sphere, and Cl3, 3 chlorine atom present outside this square bracket. So it is what? That is the ionization sphere. This is ionization sphere. So this ionization sphere satisfies primary valence of that metal or cobalt, and this is the coordination sphere. Coordination sphere. This coordination sphere satisfies the secondary valence of cobalt. Now you see how many ammonia molecules are directly attached to central cobalt? 6. Therefore secondary valence of this cobalt is 6, as well as its coordination number is also 6. And here 3 chloride ion attached to this cobalt, which satisfy its valency, means primary valence of cobalt is 3 and secondary valence of cobalt is 6. Here see, in this structure, primary valency of cobalt is 3 and secondary valence of cobalt is 6, which is equal to same, that is coordination number of cobalt is also 6. Coordination number of cobalt is also 6. So this is nothing but these are the postulates of Werners theory, which put forth first of all some points or postulates about the coordination compound. See once again, metal ions, unlike the metal salt in complexes, shows two type of valencies, that is primary valence and secondary valence. Both these valencies are satisfied by the central metal atom or ion present in that coordination compound. Primary valence is satisfied by ionization pair and secondary valence is satisfied by the coordination pair or ligand which are present in that coordination pair. Secondary valence satisfied by ligand presenting coordination pair. Secondary valence of that metal atom or ion is fixed, it is rigid, which is satisfied by ligand. There is a strong bond is present between the metal ion and the ligand, that is the coordination bond, and the primary valence is not fixed, it is variable, that is satisfied by generally the anions. Secondary valence have fixed spatial arrangement in the space of that molecule, that is, it gives the definite geometrical shape to that molecule or coordination complex. So this is nothing but example, that is CONH3 by 6 and Cl3. 6 ammonia molecules are directly attached to cobalt, therefore its secondary valence is 6, which is equivalent to coordination number, that is 6, and 3 chloride ions are attached to that cobalt, which are outside the inner sphere, which are outside the square bracket, therefore its primary valence is 3 and secondary valence is 6. This is nothing but the Werners theory for coordination complexes or coordination compounds. Next point, classification of complexes. On the basis of type of ligands attached to the central metal atom or ion, यानी क्या, वो सेंट्रल मेटल एटम को और सेंट्रल मेटल आयन को किस प्रकार के लिगेंड अटैच है, व्हाट टाइप ऑफ लिगेंड्स आर अटैच, किस प्रकार के लिगेंड अटैच, यानी क्या कि whether the ligand attached to that central metal atom or ion are same, all are same type of ligand, or they are not same. If they are different, on that basis there are two type of complexes, that is homoleptic complexes. So what are the homoleptic complexes? These are the complexes in which all ligands attached to central metal atoms are similar. यानी कि सब लिगैंड जो अटैच है सेंट्रल मेटल एटम और आयन को, वो सब लिगैंड सिमिलर है, इट इज सेम टाइप, एक सरीके है. सो दैट इज नथिंग बट द होमोलेप्टिक. होमो मीन्स सेम. होमोलेप्टिक complexes means ligands attached to the central metal atom or ion are similar. Ligands attached to central metal atom or ion are of same type. Examples you see here. For example, that is CuNH3 hereby 4 plus 2 charge present on it. So all 4 ammonia molecules are attached to copper. All ligands attached to copper are similar. That is ammonia molecule. Or here CmICO hereby 4. This is also what, that is the, it is 4 carbonyl groups are attached to nickel. Then Zn Cn by 4 having 2 charge on it, plus 2 charge. So all ligands attached to central metal atom or ion if same, then that type of ligands or that type of complexes are called as the homoleptic complexes. See, second type, heteroleptic complexes. Heteroleptic complexes. So see, heteroleptic complexes and their examples we have to study. These are the complexes. These are the complexes in which ligands attached to central metal atoms or ions are not same, are not similar. They are different. Ligands attached to central metal atom or ion are not same. They are different. Then such type of ligands are called as the complexes are called as the heteroleptic complexes. They are known as the heteroleptic complexes. For example, here CONH3, here by 3 Cl3. Two type of ligands are attached to central metal atom or ion. That is 3 ammonia molecule and 3 chlorine atom. They are not same. The ligands attached to central metal atom or iron are not same. They are different. So this is the example of heteroleptic complexes. Hetero means different. Hetero यानी क्या अलग अलग, यानी क्या different. So that species are not same. Then another one example, that is nothing but CrEn by 2. Here Cl2. That is also two types of ligands are attached. Ethylene diamine, 2 ethylene diamine molecules are there, and 2 chlorine atoms are there, chloride ions are there. So that is nothing but the heteroleptic complexes. यानी कि एकदम सिंपल है. अगर सेंट्रल मेटल एटम और आयन को जो सभी लिगैंड अटैच है वो सेम है, सिमिलर है, यानी कि एक सरीके है, तो दैट इज द होमोलेप्टिक कॉम्प्लेक्सेस. और अगर कॉम्प्लेक्स में सेंट्रल मेटल एटम और आयन को जो भी लिगैंड अटैच है वो सब सेम नहीं है, वो अलग अलग है, सो इट इज नथिंग बट द हेटेरोलेप्टिक कॉम्प्लेक्सेस. ओके, नाउ सी second type of classification of complexes, that is on the basis of the charge on the coordination sphere. Again these complexes are classified into 3 types. अगर हमने आयोनाइजेशन स्पेयर कोऑर्डिनेशन स्पेयर से अलग किया तो कोऑर्डिनेशन स्पेयर के ऊपर कौन सा चार्ज है, कौन सा चार्ज फॉर्म करता है कोऑर्डिनेशन स्पेयर. सो ऑन दैट बेसिस देयर आर 3 टाइप ऑफ लिगैंड्स. फर्स्ट वन, इट इज कैटायनिक complexes. So what are the cationic complexes? That is the net charge on coordination sphere. On the coordination sphere is what? That is the positively charged coordination sphere. Net charge present on coordination sphere is positive. So that type of complexes are called as the cationic complexes. They are known as the cationic complexes. You see this example, that is Zn Cn by what? That is the here 4. Here what? That is the 4. Then here charge present. Sorry, it is what? That is the -2. And here 1 minute, Zn NH3 by 4, here +2 charge. Net charge present on this complex is +2. Cationic complex. It is cationic complex. Then here another one example, that is the that is the Cu NH3 by 4. Here what, that is the +2 charge, cationic complex. If overall charge present on the complex is plus or the positive, then that type of complexes are called as the cationic complexes. That is known as the cationic complexes. Now see, another one example of this complex is what, that is the CO NH3 here by 4 Cl2, and what, that is the Cl. Here what happens, chlorine when form chloride ion, then here there is formation of positive charge on this complex, therefore it is cationic complex. See, the second type of complex is anionic complexes, anionic pair complexes or anionic complexes. Net charge on coordination pair, net charge on the coordination pair is negative. Whatever it, -1, -2, -3, -4, whatever it may be, but overall or net charge acquired by the coordination pair is negative, minus, and that complexes are called as the anionic complexes. Examples of anionic complexes here see K4 Fe Cl by 6, 4K plus, here there will be 4 minus, 4K plus, there will be 4 minus, or this one Zn Cn by 4 2 minus, that is the tetracyanozincate 2 plus. So 2 minus charge is present on this complex, therefore it is nothing but the anionic complexes. So complexes which have net charge acquired by the coordination pair is negative, that is the minus, and that complexes are called as the anionic complexes. They are known as the anionic complexes. Or you take this example also, Na Ag Cn by 2. Here what happens, when this Na gives Na plus ion, then here charge will be minus and it will be anionic complex. It is anionic complex. Third and last type of complexes are, that is the neutral complexes. Neutral complexes. So what are the neutral complexes and their examples we are to study? The complexes in which there is no any charge on coordination pair, no any charge on the coordination pair, they are known as the neutral complexes. They are called as the neutral complexes. You see the example NiCO by 4. Here no charge on this complex. Then second example is what, that is the CO NH3 by 4 Cl3. There is also no any charge on this complex. It is neutral complex. This is the neutral complex. So this is nothing but the classification of complexes on the basis of the net charge acquired by the coordination pair. If coordination pair have positive charge, they are called as the cationic complexes. If net charge on the coordination pair is minus, negative, then they are anionic complexes. And if there is no any charge on the coordination pair, then they are called as the neutral complexes. They are called as the neutral complexes. So this is classification on the basis of type of ligand, two type of complexes, homolyptic complexes and heteroleptic complexes. And on the basis of charge on coordination pair, there are three type of complexes, cationic complexes, anionic complexes and the neutral component.